but I wasn't going to change the problem in midstream. All right, well, I am leaving on Sunday for some work-related travel and then Thanksgiving. I don't promise to have it graded until after Thanksgiving. Chances are I won't because I have 2 big grant proposals due. Yeah, that's the least fun part of my job. Anyway, but so a few important end of the semester discussions announcements. So I will be posting the next problem set, and that will be due on Tuesday, although there will be no lecture, okay? I will be here on Tuesday. So there's no lecture. And then I will be distributing final problem set, which will be due, I wanted to have it due right after Thanksgiving, be a longer assignment and more time. It'll be due the last day of class, okay? Well, not the last day of class, the last day of classes. It'll be due on Friday, the 5th at the usual time. We'll have an additional problem session for last minute questions on the 5th, okay? Because I won't be here next Tuesday, come on in. We won't have lecture, but I would like to have a makeup lecture on Wednesday in the evening, okay? And I will be giving a quote-unquote bonus lecture for those who are interested, where we'll talk about bells and volleys and entanglement. Something we won't be able to get to in time, so everyone should have a chance to see that. So, now I also want to talk about the final exam. Question mark. The final exam is scheduled firstly at 7:30 in the morning on Tuesday. Forget that. We're not going to do that. Good. We'll see you here. Enjoy. I'm up, but I'm a mean guy, but that's just the thing. So if the final, I don't want to have that. However, there's another question. Should we have a final exam? I think, been thinking about this, that don't think we can make the final optional. Meaning that I'll assign you a temporary grade based on this material, the exam and your homeworks, and you can take that, and I will base that on redistributing the final scores. I'll reassign the homework and the weightings for that. And if you're okay, you don't have to take the final. But if you want to, you can take the final and it'll just be averaged in according to the scores that were suggested at the beginning. Okay? You okay with that?
Would it hurt us to take the final then?
It could.
Okay.
It could, because I mean, it will be averaged according to the score. What was originally suggested, and that final will be given at the last day of finals. Okay. All right. So that's what we will do. All right, very good. So last time we had derived algebraically the eigenvalue associated with angular momentum in quantum mechanics. And it was based on this Lie algebra that we discussed, the generators of the rotation group in quantum mechanics. So when we do that, we introduce these important operators, J plus and J minus. And so the algebraic relation, the commutation relations, are often expressed not in terms of the components of x, y, and z, but j plus and minus and jz. Okay? Right. So what we showed last time was that the simultaneous eigenstates, so what we call the standard basis, are the eigenvectors that are simultaneously eigenvectors of these two operators. They form a mutually commuting set. That's the standard basis. We could have chosen any component along any direction in space that also commutes with j squared. But this so-called standard basis are the eigenstates that are simultaneous eigenstates of the magnitude squared at jz. And these are the familiar eigenvalues, right? So what we have from this expression, because these guys are also eigenstates of j squared, that the eigenvalues m range from the value minus j to plus j in integer steps. So there are two j plus 1 different eigenvalues m for a given j. And that means, since this goes in integer steps, that j can be either an integer or a half integer. And the operators j plus and minus are the ladder operators, or the raising and lowering operators in angular momentum, whose action is to raise or lower the m value, the eigenvalue of kz, by either plus 1 or minus 1. Right? Now, one thing we didn't mention last time is that, generally speaking, this is not a unitary operator, right? I mean, it's this. And so, in general, its action on a ket will not preserve the norm of the vector. So there's some constant out front, like we had with A and A dagger, right? For the Fock states, you get a square root of n or a square root of n plus 1 out front when you act on it. So what is this constant? Well, to find that, we just have to look at what the norm is. I mean, we can only determine this up to an overall phase. The overall phase of this is always arbitrary and decided by convention. Yeah?
Is it different for different expressions of j and m, or is there just some expression like j times j plus 1?
Yeah, there's some expression, and that's what we're going to derive right now. So how do we do it? We want to take the norm of this vector. So if we look at that, we have j m, let's get a better usage of, maybe. J m j minus, let's do it this way. So that's the inner product of this vector with itself is equal to the magnitude of this constant squared, okay? Assuming these are normalized vectors, right? Now, of course, j plus dagger is jx dagger minus I jy dagger, right? And these are Hermitian. So that's J minus. And J minus dagger is J plus. So what that tells me, this then is, tells me that this is equal to J minus plus times J plus minus acting on this. Right? So this is, how do we deal with this? Well, we got these relations which are handy-dandy as an adverb written over here. And so we have J plus times J minus is that, and J minus times J plus is this. So that then is equal to J and J squared minus JZ times JZ plus or minus 1 . All right, so now what?
We know the eigenvalues.
We know the eigenvalues. So JZ acting on this gets replaced by n. J squared acting on this gets replaced by what? J times J plus 1. So this then is equal to J times J plus 1 minus M times M plus or minus 1. And that is equal to the norm squared of this constant. And thus we see that, and by convention we choose this to be positive. I'm just going to cut you off there. You need it. All right. We have the relationship that this is equal to square root of J times J plus 1 plus, or I'm sorry, minus M plus or minus 1 acting. Okay? So the convention is to just choose it to be a positive real number. All right? So does this have the right behavior? What we expect is that when J plus acts on the stretch state, the state where M has its maximum value and the maximum value of M is equal to J, what should this be when I raise the maximum value? 0. I annihilate it. And similarly, it must be the case that when I apply this to the stretch state with the minimum value, I should also annihilate it, right? Because we said M can't get bigger than J. That's how we define J, to be the maximum value of M, or minus J to be the minimum value of M. That's how it came out algebraically last lecture. And does that work? Indeed it does, right? If M was J, and then I apply the plus, this would cancel. And if I apply J minus with M equals minus, this would also annihilate it. So it all hangs together as it must. Yay, math. All right. Very good. As I had drawn here, what this says is that we can think about a kind of picture of possible angular momentum vectors that are allowed in quantum mechanics as a kind of picture that back in the ancient days of the 20th century, early 20th century, was called space quantization. Although it's an arcane term that I think is rarely used, but you'll see it occasionally. Which means that the projection of angular momentum, if I have an angular momentum, says that the magnitude squared of angular momentum, if I'm in an eigenstate, is jj plus 1, right? So here's a sphere that has that radius. Okay? So that's the magnitude of the vector. But its projection onto some axis, which we call the z-axis, is m. But the projection can't take on arbitrary values for a fixed j value. It takes on discrete values. And then the x and y component is not certain. It is uncertain, right? It is uncertain because I cannot simultaneously specify the x, y, and z components of angular momentum. I can only simultaneously specify the magnitude and one component. Okay? And so we think about the eigenvectors of angular momentum as kind of a vector that lies somewhere on this cone that the vector lies somewhere on that cone, but I don't know where. Okay? And then we have different possible quantizations. It can never be exactly pointing along the z-axis, because then it would have a definite z value, and a definite x value, and a definite y value. So there's a maximum possible value here. Right? And this is m equals j. And then there's, the next guy.
That's m equals 1.
I'm sorry, I said j, but I wrote 1. I don't know what parts of my brain are connected and which ones aren't, but I'm sure they're not all connected together, right? And then I would have this. So this is, what is j in this case? The way I drew it. So this is, it's got 1, 2, 3, 4, 5, 6, 7.
3.
So this is 7, right? 3. So this is n equals 3, m equals 2, m equals 1, m equals 0, m equals -1, m equals -2, m equals -3. It's supposed to look symmetric. Right? This is supposed to have the same size as that. Notice that the state that has the maximum or minimum projection of angular momentum along the z-axis has the minimum uncertainty in x and y. Okay? How can we see that that must be the case? Let's think about the uncertainty principle. So what we have here is that delta jx squared times delta jy squared is greater than or equal to h bar squared over 4, the expected value of jz. Squared. Right? That came from our usual delta a squared, delta b squared is greater than or equal to 1/4 the expected value of the commutator of a with b squared. Okay? So that's the Heisenberg-Robertson uncertainty principle, as it's sometimes called, and this is the particular case for angular momentum. Or in terms of our dimensionless variables, if I take the square root of everything, that would be y greater than or equal to 1/2 expected value Now, one thing we can say, firstly, is that I claim it's obvious the following things are true. There are many ways to show this, but I claim it's obvious that the following things are true. That in the standard basis, firstly, I claim this is true. The mean value, not looking at this picture, although that picture might be taken. I mean, it's obvious from that picture, but where did that picture come from? So that if I'm in an eigenstate of, that's a simultaneous eigenstate of j squared and jz, then the mean value of jx and jy must be 0. Why? Anyone have some suggestions?
It's because when you do it, if x and y are composed of plus and minuses, and when you do it, you end up with m and m plus 1 and minus 1.
Excellent. Okay, so that's a good way of looking at it. So what Stephen was saying is that we know that jx is j plus j minus over 2, and jy is the anti-Hermitian part, which is j plus minus j minus over 2i. Right? And when I insert that in here, then I'm going to either raise or lower m by 1, and then that's orthogonal to that, right? So right? They're orthogonal vectors. Similarly for that. So that's one way of looking at it, and that's certainly correct and a good way of looking at it. Another way of looking at it is the following. These vectors are the standard basis are eigenvectors of rotation about the z-axis. Okay. Remember that our rotation operator about the z-axis was I rotate by some phi by jz. Like that. Use me. That, right? So if I insert something that rotates this, it's going to keep it invariant, but it's going to move the x into y and y into x, right? The only way that that expectation value, because these guys are not eigenstates without rotation, this must be 0. Just another way of looking at it. And so I claim from this perspective, another thing is true, that for an eigenstate in the standard basis, the uncertainty in x must be equal to the uncertainty in y, because it's rotationally invariant for that state. Okay? So, with that said, we see immediately the following picture. What is this uncertainty? Well, the uncertainty in x squared is equal to the uncertainty, is equal to the expected value of jx squared minus the expected value of jx squared. That's 0. Okay. This is a half of that
should that be plus and minuses?
Sorry?
Should that be plus and minuses for x?
I don't know what you mean.
Like,
The uncertainties of this is the expected value of jx squared minus the square of the mean value.
yes, but you wrote j squared in terms of jx and jy, should it be in terms of j plus and minuses?
No, what I'm saying is the following. That this is equal to a half of the uncertainty in x plus the uncertainty in y, because they're equal. Okay? So when I've written this over here, what I'm saying is that because of this, I can do this. All right? And what's that?
J squared minus JZ squared.
Exactly. That's j squared minus the z component squared over 2. Okay? Because jx squared plus jy squared plus jz squared is j squared. So that's equal to j plus 1 minus m squared over 2. So we've learned here that for the eigenstates, the standard basis eigenstates, the uncertainty in x is equal to the uncertainty in y is equal to the square root of j times j plus 1 minus m squared over 2. Okay? So, notice that this uncertainty gets bigger as the magnitude of m gets smaller. So the minimum value of this is what? Well, that's the case when m equals j, or m is plus or minus j, because it's m squared. And then that becomes the square root of j over 2. That's the minimum uncertainty. That's, excuse me for a moment, but this uncertainty is just, and you can see that geometrically, just from looking at this cone. So this is the square root of j over 2. These cones just tell the whole story, really. Well, we did it all algebraically. And what's the maximum value? I'll call it j perp, because it's the direction perpendicular to. Well, that's when m equals 0, right? And that's equal to the square root of j times j plus 1. Are any of these states minimum uncertainty states? Meaning, do they saturate with equality the uncertainty relation? This is the uncertainty relation. Or do any of these states satisfy this relation? So let's see, delta jx times delta jy is equal to that over there, right? And I want to know, is it ever equal to this?
M equals to j?
Yes, indeed, good job. When m equals j, the stretch states are minimum uncertainty states. These states near the poles are the most localized you can be. Okay? These states, the states that are at the poles here, are sometimes called spin coherent states. as opposed to the harmonic oscillator coherent states that we talked about. They're like minimum certainty spin wave packets. They're kind of the closest thing in quantum mechanics we can get to being a spin sort of pointing in some direction, or a spin or an angular momentum. Spin, or it could be orbital too. And in fact, if I rotate the maximum projection along any way, that's a spin coherent state. It's like the displacement operator, but now instead of displacing it, I rotate it on the sphere. All right, very good. Okay, so let's talk now about representations of the operators. Well, the standard basis is this. So let's talk about what our operators look like in a basis. So the standard basis, the joint eigenstates of J squared and Jz, where J can be 0, a half, 1, 3/2, 2, etc. And given that, m goes from minus j to j in integer steps. Okay, that's my basis. Okay. What can we say? So what I want to look at is, I want to look at the operators I want to look at are j squared, jx, jy, and jz. Let's look at the representations of those operators in this basis. Well, firstly, these guys are diagonal, right? So if I look at, j squared, well, firstly, what we see here is that it's natural to arrange the basis in blocks. Each block is a 2j plus 1 by 2j plus 1 block for all the different m values associated with a fixed j, right? So, the first eigenvalue obviously is 0. That's for j equals 0, it's jj plus 1. And then I have, what's the next eigenvalue? Well, it's a half times a half plus a half. A half times a half plus 1, right? So that's 3/2 times a half, or 3/4. And how many different m's are there associated with j's a half? 2, right? Second half and a half and a half. I'm sorry. 3/4 and 3/4. Right? For this guy. And then I have a 3 by 3 block. That's 1 times 1 plus 1, which is 2. Etc. Then I have a 4 by 4 block, a 5 by 5 block, etc. Yes?
So, I mean, does that come from the degeneracies or no?
Indeed.
Okay.
Indeed. So there is a degeneracy here. All because all the states, all those states that I've kind of drawn as vectors, they all have the same magnitude, but they don't have the same projection. Jz, in this case, of course, for the J0, Jz is also 0. What are the possible values of jz for j equals a half?
Minus a half and plus a half.
Minus a half and plus a half. Now, it's never clear to me what's the standard order, but the standard order I'm going to take is to put the plus, go from m equals plus j to minus j in intercepts. And then the 3 by 3, m goes 1, 0, minus 1. And zeros everywhere else. Not that bad. Okay. What about jx and jy? How are we going to express them in the standard basis? They are not eigenstates. We kind of had a hint over there. Exactly, the raising and lowering operator. So that's the key to remember. Whenever you're dealing with x and y, terms with j plus and j minus. Okay? So let's just look at each block separately. Of course, again, so when j equals 0, everything is the 0 matrix, so it doesn't really matter, right? Jx is the same representation as jy. It's just a 1 by 1 matrix with a 0 entry. It's the only thing that happens, right? When j is a half, well, so we need to look at, let's look at the representations of j plus and j minus in the standard basis, and then we will combine them in Hermitian and anti-Hermitian combinations to get jx and jy. So this acting on the state j equals a half, and we put half is y. Well, this is the state with the maximum projection, and I raise it, so what do I get? 0. X. J minus acting on this, well, this is something times both sides with n equals minus a half. And that is the square root of a half times a half plus a half, I'm sorry, plus 1 minus a half times a half minus 1, right? According to the beautiful rule over there, a half minus a half. So that is equal to what? Well, the half times the halves cancel that. That's a half plus a half. That's 1. In this case, hooray, there's no prefactor. The raising and lowering operator takes spin up to spin down with no prefactor. And j minus, you can go through the same algebra. I mean, j plus takes spin down to spin up with no prefactor. Okay. So what that tells me is that j plus is equivalent to that matrix in the standard basis, ordered m equals plus a half, m equals minus a half, and j minus is that matrix. Okay. What are jx and j minus for j equals a half?
Jx and j minus.
Jx is the sum of j plus j minus over 2. Okay, in the standard basis. And jy is what? Right, this is jx is j plus j minus over 2, and jy is j plus minus j minus over what? 2i. real and imaginary parts. These guys look familiar? Yeah, we'll come back to those. Of course, the Pauli matrices don't have the half in them. There's sigma x's, but you know, there's too many factors. But we'll come back to that. Alrighty, and then we can go for the case. I don't want to screw up the algebra, so I'm going to look at my cheat sheet. Yeah. So for spin 1, or j equals 1, this could also be orbital. There's no reason it's still true, right? This is still a basis. Jx is something you've all seen. They're the same J's. Right? And that comes from doing exactly that algebra. Should we do one of them just to see how that works out? Or you're happy?
You did that on the exam.
You didn't do the J plus and J minus thing though, right? Just for brains, because let's just look at J plus. Let's look at the representation of J plus for J. Okay? What happens if I look at this on 1, 1? That's 0, right? Annihilates it. J plus acting on this. Well, that's the square root of 1 times 1 plus 1 minus n times 0 times blah, 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 0 times 1, 1. Right? And so that's the square root of 2. And J plus acting on this, square root of 1 times 1 plus 1 minus 1 times 1 minus 1. So that's 0 again. So that's the square root of 2 from 0. You gotta do all those square roots and do it right. And so what do we get? What is the representation of J plus as a 3×3 matrix in the subspace J equals 1? All of its diagonal elements are 0. So let's just, for writing this in the search order, this is 1, 1, 1, 0, 1 minus 1. All the diagonal elements are 0. Right? Row 1, 1. 1, 0, that's root 2. But this guy is 0. Root 2. 0, 0, 0. Okay? What's J minus? How could you find it instantly?
Take the dagger.
Take the dagger, thank you. And how do you take the dagger? Transpose conjugate. Well, it's the same thing in this case. But that can't be right.
But you divide by the I.
No.
Get Y.
Root 2 should be on
No,
third.
I screwed it up. Where did I screw it up?
The root 2 should be on the third column.
On the negative and the J plus reactive.
Oh, wait, hold on a
It
second.
should be the upper triangle.
Row
That's be a zero.
Yeah, that's a 0, that's a 2.
No, yeah.
Hold on.
It's
2 or 3.
That's for two.
That's a 2. This goes to -1. Yep. Sorry.
Okay.
Yeah, that's correct. Sorry.
So, I mean, they're kind of like the equation of analysis.
They are. That's what they are.
Form, yeah, okay.
They are the same form.
Okay.
And so this is root 2, 0, 0, 0, 0, 0, 0, 0. You add these together, you divide by 2, you get that. You subtract these, you divide by 2i, you get this. Okay? That's where they came. All right. So that's the representation in the standard basis. Now, for the particular case, for J integer, there exists orbital representations. Which we typically call L. So let's talk about that. So when J is an integer, we talk about the standard basis Lm. Okay? Where Lz, right, that's equal to H bar, where this is xpy minus ypx over h bar. We're talking about motional angular momentum, orbital angular momentum. This has, and there's an L squared on this, it's still LL plus 1, and LZ acting on this is and goes from minus L to L in integer steps. Okay, just as before, it's just I called it L, and this is what it is relative to x and p. All right. Now, there is, what Hilbert space are we talking about? In the context of orbital motion, we had talked about this, the Hilbert space for motion of a particle in 3D is the space of square normalizable functions in 3 real dimensions. That's our Hilbert space. Okay? And this Hilbert space we decompose as a tensor product space in many ways. One way we said is that I can separate it, think about it as a Hilbert space associated with the radial motion and a Hilbert space associated with the motion on the sphere. So, so what are these spaces? What are we talking about over here? What are these Hilbert spaces? So, if I think about, my L2R3 wave functions are integrated over all space. Let me call it d cubed x. Well, we typically normalize them. Normalize them not to 0. 1. That would be terrible. Okay. Now, when we're talking about, if we're separating in this way, then of course what we're doing is we're writing this d cubed x as r squared dr d omega. Okay? So we are talking about now breaking up three-dimensional space into spheres where we have a little volume element here has a dA, which is r squared d omega being the element of solid angle, and we have a little dr. Okay? So, if we're talking about a product space like this, let's think about a state that's a product state which has a support that's only has a wave function that exists in this space and a product that exists in this space. So let's consider a product state of some radial wave function and some angular wave function. Let me call that angular wave function upsilon. Who doesn't like upsilon? Which is a function of that. Okay? Squared. Okay? So our space here, so if upsilon as a function of a solid angle is in this Hilbert space, then it is normalizable when I integrate over all solid angles. Okay, so we're looking at functions which are normalizable on the sphere with the usual d omega being sine theta, d theta, d phi. Right? Now, whenever you're doing an integration over the sphere, you always should rewrite this as d cosine theta. Always. Never, ever leave the sine theta. Because this is the natural coordinates. Of course, this is minus. So really, I should think about this as a function of cosine theta and phi, rather than of theta and phi. Always. And so my integral goes over what values? If theta goes from 0 to pi, cosine theta goes from -1 to plus, or minus cosine theta goes from -1. So this integral is an integral -1 to 1 d mu d phi, where mu is cosine theta. Whenever you're doing angular integrals, always make that change of coordinates. Okay. All right, so that's the space we're talking about. And we can then talk about position on the sphere. So we can have a resolution of the identity in terms of position on the sphere, angular position. So there is a resolution that looks like this, where this is my shorthand for theta phi, or cos theta and phi. Okay? Notice, so these guys satisfy this, which is on the sphere, this is the delta function. cosine theta, not theta. Which, using the rules of the delta function, 1 over sine theta delta. Theta phi. Gotta love your Jacobians. Not if you gotta, but you should.
It's not an absolute value. We pulled out.
Yeah, I guess that must be true. Must be true indeed. Never use it, so I forget it. Alrighty, so we have this position representation on the sphere of our eigenstates of angular momentum. Excuse me. So if I have an eigenstate, or in our standard basis, our eigenstates, simultaneous eigenstates of L squared and LZ, and I want to look at them in the position representation, these things have a name. You know what they are? They're the spherical harmonics, right? So these are the YLMs as a function of that, right? Which of course separates into some normalization constant times the associated Legendre polynomial, which of course is only a function of cosine theta, because on the sphere everything's just a function of cosine theta, not theta alone. And e to the I and phi. Now we already saw this lectures ago. We already derived that the eigenfunctions of LZ were this form. Right? These are the more general case. Of course, we have completeness. Well, first of all, we have orthogonality. That is to say, we know that eigenvectors associated with the complete set of eigenvalues are orthogonal. Right? So that means we can write this expression as an integral over the sphere by inserting our position representation for the sphere inside there. That's the resolution of the identity, which tells me that this is the integral Lm this L prime M prime. And this is equal to integral y Ln star theta, or theta phi, y L prime n theta phi. So when you integrate this over the sphere, that means these are orthogonal. Clearly that's true. The two pieces are independently orthogonal. That's to say, the eigenstate for a fixed any value of L, the different states for different M are orthogonal integrating over all phi, right? That is to say, if I look at this, I could break it up into an integral over phi, e to the I minus I and minus n prime phi, integral d mu normalization constant squared p L prime n prime mu p L m, right? And this is a delta function. I think actually this normalization constant doesn't depend on m, only depends on L. So let me get rid of that. And for a given this then, when this n is n prime, this is delta L. What's I say? M equal to n prime. So they are orthogonal functions on the sphere. They are also complete functions on the sphere. What does that mean? Well, we know that the set of eigenvectors span our Hilbert space. They span the Hilbert space I called H theta phi. They are a complete basis, right? So what that means is the functions, well, I could say a few different things. It says if I have, let's suppose I have some epsilon that's in my space. Okay, some vector that lives in this Hilbert space. Well, then I can express this vector by inserting the complete set of states right? And this is some set of coefficients. So what that tells me is that if I look at this in the position representation, that I can always take any function that lives on the sphere that is square normalizable on the sphere and express it as a Fourier series of spherical harmonics. The set of spherical harmonics span the space, and you can think about them as like Fourier components. Do you have a question, Zeke?
Just real quick, I mean, I guess kind of answer, but you know, the epsilon here.
Yeah.
I mean, so that's this really general. It doesn't. I thought it was going to end up to be this spherical harmonic.
It's anything.
Okay.
It's any function that lives on the sphere, function of position at some direction in space, such that that function is square normalizable. Such functions can always be decomposed as a superposition of spherical harmonics, where those coefficients are the projection of the spherical harmonic onto epsilon. So this tells me the projection of this function onto the YLM. Is that clear? So, two other things to say about spherical harmonics. So the spherical harmonics satisfy the following properties. If I look at the complex conjugate of this function, what I get is this with the minus m. And there's the way the phase convention works, there's a minus 1 to the m. That's clear here. You see, if I take the complex conjugate of this, m goes to minus m, right? And then there's just a question of what happens, what are the associated Legendre polynomials in that case. This particular convention is known in physics as the Condon and Shortby convention, but whatever. The other property another property I want to measure is parity. So parity is sending the position vector x to minus x, right? Well, what that means in this case, if I look at the sphere, is I take theta and turn theta into theta plus pi, and then phi go to minus phi, right? So if I look at that, the question is what happens to these things? Well, PL, if theta goes to theta plus pi, then cosine theta goes to minus cosine theta. And the Legendre polynomials are antisymmetric for odd L, and they're symmetric for even L. So what this tells me is that under parity, the YLM goes to minus 1 to L YLM. That's to say, the YLMs are eigenstates of parity with this eigenvalue. The even L's are even parity. The odd L's are odd parity. Now, why must it be the case that the YLMs are eigenstates of parity? Well, remember that certainly L squared is invariant under parity because this is the square of a vector and the vector goes back to itself. So this is invariant under parity. And LZ is x py minus y px, right? And what happens under parity to this? Well, x goes to minus x and p goes to minus p. So this goes back to itself. So under parity, sometimes an angular momentum vector is known as a pseudo vector because it does not invert under parity. X and p invert, but angular momentum doesn't because it's a product of x and p. So eigenstates of this are also eigenstates of parity because they are invariant because of that symmetry operation. Okay. All right. I guess we kind of ran out of time, but I'll say one thing here, and then let's just write down a few of the YLMs. So y00 is a constant. and it's normalized over a sphere. It must be the case that when you square these guys and you integrate over all 4 pi steradians, you get 1. That's that. Y1 0 is equal to the square root of 3 over 4 pi cos theta, and y1 plus or minus 1 is equal to the square root of 3 over 8 pi sine theta e plus or minus I phi. Minus plus over. And just remember those for a reason you'll see why you can possibly remember that. Now, then there's, I can kind of write down the others. Go to 2.
They have cosine and sines.
Yeah, they do. Now, there is an important thing I want to say here just to conclude this. Let's look at, let me define what I'm going to call the solid harmonics. To be a function of position as the radius squared times the y-ln function of theta and phi.
R squared.
Sorry, no, r to the l. R to the l. Let's define that. Let's see what those functions look like. Well, y0, 0 is still the same. I didn't do anything. y1, 0 as a function of position is equal to square root of 3 over 4 pi r cosine theta. And y1 plus or minus 1 as a function of position is the square root of 3 over 4 pi r sine theta over 2, plus or minus 1, which I'll write out as sine phi plus or minus I cos phi.
Z and Y and X.
Exactly. Very good. Very good. So everyone should have in their head how x, y, and z are related to r, theta, and phi. Everyone should have that in their head. So, if I look at the picture there, z is equal to the projection on the z-axis by theta. That's just r cosine theta. Projection onto the xy plane is sine theta, and then you have cos phi and sine phi. I know it's a lot to have in your head, but that's the way life is as a physicist. That's what makes us physicists. Okay? So, we see the beautiful relations that we're going to explore a little bit more. We didn't, I thought we would finish this, but we didn't. This is Z. And what's this? X plus or minus IY. Remember that. I said remember that. There's a minus plus here. This is minus plus X plus or minus IY over root 2. These are the spherical harmonics that I always remember. Because these, as we will emphasize, are polynomials, in this case, first order polynomials, in the basis of x plus or minus iy and z. The basis x plus or minus iy and z are the natural coordinates that are the eigen functions of rotation. Okay? these are called spherical tensors, and they're going to play an important role next semester. And a very important role when we talk about the Bigger-Eckhart theorem and everything about selection rules. So we're going to emphasize this a little bit more next time.
Don't forget hydrogen.
Oh yeah, boy, hydrogen. Where's my pen?
Look at that,